Okay, so today's lesson is a new topic for this unit. It is refraction. We have already looked at reflection earlier. Of course, refraction is the bending of light. This is going to go into it in a little bit more detail. Okay, so by the end of this unit of this topic, you should be able to investigate the refraction of light, and we're going to do that by experiment. We're going to know and use the relationship between the refractive index, angle of incidence, and angle of reflection to do some calculations. And we'll do it also in the experiment. Investigate the refractive index of glass using a glass block. Again, experimental. Look at the role of total internal reflection in the transmitting of information along optical fibers and prisms. And explain the meaning of the critical angle. Okay, and also know and use the relationship between the critical angle and the refractive index. And finally, know that sound waves are longitudinal waves that can also be reflected and reflected, which we've already looked at in a little bit of detail. Okay. So what is refraction? Going back to our previous lessons, simply refraction is the bending of light when it travels from one medium to another. Okay, so you can see in this particular glass here, you have the straw. Essentially, the straw looks like it's going to be split in half. That is due to the bending of the light as it enters from the less dense air into the denser water. Okay, so a medium is either glass, air, or water, possibly plastic. Okay, it's just how the light is traveling through. Okay, even could be a vacuum for light. Okay, so let's look at the interface in a glass block between air and the glass itself, which will be part of the experiment as well, and usually comes up as a question in exams. Okay, so light passing through the glass block is at right angles to the surface, will not be refracted. These ray lines will be just passing straight. Okay, so again, just as we did with reflection, we have a normal line, which is going to be exactly orthogonal or 90 degrees to the interface between the air and the glass block. Okay, this interface here, where the air meets the glass. Okay, so just like in reflection, we have an angle of incidence between the normal line and the incident light ray. We also have a refracted light ray. Notice where it has been refracted or bent, and correspondingly there is an angle of refraction between the normal line and the refracted light ray. So when passing from a less dense medium, so for example air, to a more dense medium, in this case glass and the glass block, light bends towards the normal. Okay, so when it's going from less dense to more dense, it's going to bend towards the normal. And on the way out, you're going to notice that the ray emerges from the block parallel to the original direction. Okay, so it's going to be parallel to the original direction. So why is light being bent? Well, we kind of looked at that earlier in the unit when we went outside and did that little experiment, moving at different speeds. Okay, so light is made up of tiny little waves, okay, at least for the purposes of this experiment. You've already looked at this previously in a previous presentation, how it does get bent. So when light beams pass through the air into glass, one side is slowed before the other, and this causes the light beam to actually bend. Okay, that you see in the animation. So let's connect the learning now. Okay, so what happens as a ray of light enters a glass block? It bends towards the normal. Why? Because the speed of light changes. Okay, it slows down. So now look, a practical application could be in fishing. Okay, so if you look down into a fish bowl, the goldfish looks actually closer to the surface than it actually is, because the light is being bent. Okay, and this is based around the concept of a refractive index. Okay, the refractive index of a medium, in this case glass to water, is defined by the speed of light in a vacuum divided by the speed of light in the medium. Okay, so here is a different range of mediums and their associated refractive index. And the equation is the refractive index equals the speed of light in a vacuum, which is 1, divided by the speed of light in the medium. Okay, so as soon as it hits a medium, it's going to slow down. Right. Refraction of a light by a prism is known as dispersion. So white light goes in and it refracts. And it's going to divide into the 7 different colors. This effect is called dispersion. Okay, and we see this in this image here. It happens because white is a mixture of all the colors in the rainbow. Okay, so we've looked at the refraction in a full block, but also reflection of light can occur in a semicircular plastic block. Okay, so that yellow part is all now full of plastic. And just like in the previous example with the full block, you have a refracted ray, angle of refraction from the normal, an incident ray, and an angle of incidence also from the normal. Okay, so when a ray of light travels through a semicircular block, its ray will be refracted. But there is also some slight reflection from the surface or the interface between the plastic block and the air. Okay, as the incident ray approaches the critical angle, approximately 42 degrees, and we'll look at critical angles later in the unit, the refracted ray travels at right angles to the normal. This is now known as more internal reflection. Okay, so continuing on with the refraction of light by a semicircular block. So if the incident ray, okay, this one here, now enters the block at the angle greater than the critical angle, at least with this plastic block, of 42 degrees, no light is refracted. Okay, you see it's all being reflected. Okay, there's no bending of light over in this direction. Okay, it's all being reflected. So this is known that all the light is now being reflected at the boundary between the plastic and the air. This is known as total internal reflection. Okay, and that's an important concept, especially in fiber optic technology. Okay, so here are a range of different critical angles for different mediums. So between air and water, it's 49 degrees. Between air and a plastic known as perspex, it's 42. So your plastic blocks are made of perspex. Between air and glass, it's 41 degrees. And for air and diamond, it's 24 degrees. Okay, so you can use total internal reflection in periscopes. Okay, that's quite useful, especially in submarines, for example, or at rock concerts when you can't stand and see the rock concert band. Also used in bicycle reflectors, as you can see there, and finally in the bicycle reflector there. Okay, just breaking it down slightly into the smaller parts. Okay, so other examples of total internal reflection are the use in prism binoculars, okay, which allows us to have small binoculars because you're using the angle to decrease the size of the lens, and also the telescope kind of part of the binoculars. There we go. So that's the example there, how it works. Okay, so basically you're decreasing the length required because you've got total internal reflection in these kind of prisms inside the binocular. And also finally, in fiber optic cables, which are used to transfer information in terms of light, and they're very thin, flexible rods, or transparent plastic or glass, and they're used usually to send internet data or telephones. Okay, so it just is a very efficient way of sending information. So just looking at optical fibers in a little bit more detail, so there might be questions around optical fibers in a little bit more detail in the exams. So light is totally internally reflected in these fibers, and therefore there's very little loss of information from one end of a fiber to the other. We see that in a little bit more detail as we go into one individual fiber. The light enters the optical fiber and is totally internally reflected along the line of the fiber itself. Okay, so the advantages are it carries more information than ordinary cables of the same thickness. They aren't as weak as those who by ordinary means, and it's used to carry telephone calls and computer data, and also endoscopes, which is the last part of the slide. An endoscope, long thin bundles of the optical fibers which you put down into your stomach because they can bend and you can see inside your stomach and your large intestine to see if anything's wrong so the doctor can diagnose. Okay, let's do some refraction calculations now because we have some angles of refraction, we have some angles of incidence, even if you're using both the whole plastic block or the half circle block. Okay, so this is where we've got the idea behind Snell's law. Okay, so when light is refracted, an increase in the angle of incidence produces an increase in the angle of refraction. Okay, so we discovered mathematically that the sine of the angle of incidence divided by the sine of the angle of reflection is going to be a constant. So therefore, if you are using a plastic block, say the sine 15 degrees over the sine 10 degrees is going to give you a value of 1.5. Okay, if you change the angle of incidence, it's still going to be 1.5. Okay, so we've changed it to 45 and we still get a ratio between the angle of incidence and angle of reflection of 1.5. And that continues on even if we change the angle of incidence to 60 degrees. Okay, the ratio of the sine of the angle of incidence is going to over the angle of refraction is going to be the same. Okay, this is known as Snell's law. And this is where refractive index comes in. So we were discussing refractive index earlier, the ratio of the speed of light in a vacuum compared to the speed of light in a medium, okay, how it slows down. Okay, the refractive index is sine I over sine R. Okay, so if the refractive index of water is 1.33, what is the angle of refraction going to be? Okay, it's going to be essentially a rearrangement of the equation to give sine R is going to be the sine of the angle of incidence divided by the refractive index. So it's going to give you 0.532. You then take the anti-sine of R to give you the angle, which is going to be 32 degrees. Okay, it's kind of rearranging the. So again, continuing on with the refraction calculations, we can then integrate this with critical angles and total internal reflection, which we looked at earlier. And if the angle of incidence is greater than the critical angle, we will get total internal reflection. Okay, we've already looked at that. And if the ray direction is reversed, the angle of incidence is now 90 degrees, and the angle C, the critical angle, is now the angle of refraction. Okay, so you can rearrange the equation. So the refractive index is going to be now the sine of the angle of incidence divided by the sine of the critical angle. So in this particular case, it's going to be sine 90 degrees divided by the sine of the critical angle. You can then determine, knowing that the refractive index is the sine of the refractive, the ray angle of incidence divided by the sine of the angle of refraction. So rearranging that, we now know that refractive index is going to be 1 over the sine of the critical angle, or another way to write that, if you rearrange it, is the sine of the critical angle is going to be 1 over the refractive index. Okay, so we know now the critical angles for pretty much all the different mediums that we're going to be using. So if the refractive index of glass is 1.5, then that means that the sine of the critical angle is going to be 1 over 1.5, or 0.67. So using your calculators, you can then determine that C, the critical angle, is going to be 42 degrees for glass. Okay, the refractive index of a medium is usually denoted as lowercase n. So therefore, for a medium, the refractive index n is going to be the sine of the critical angle divided by 1 over the refractive index of that medium. And for example, what is the critical angle for diamond if the refractive index is 2.42. Well, the sine of the critical angle is going to be 1 over the refractive index of the medium, 1 divided by 2.42, 0.413. So that's going to be the sine of it. So take the anti-sin sine, and the critical angle of the diamond will be 24.4 degrees.